I am Mr. True. In my second video about graphing conic sections, we're going to turn our attention to hyperbolas, where we take these three-dimensional cones and we're going to slice them parallel along their axis, and thus get a pair of kind of look like parabolas that are opposite of each other, but they are not the same shape as parabolas. So we don't have just stacked parabolas opening in opposite directions. We have a pair of hyperbolas. We're going to move the screen out of the way. We're going to talk about the basic structure of hyperbolas, compare them to ellipses, and then do 3 examples of graphing them. I am Mr. True. Take 2 in my portion of this video discussing the basic structure of hyperbolas. And thank you for one of my students pointing out that I had a little bit of a mental lapse. So even though part B here says I don't care, I do. Let's point our attention first to the horizontal hyperbola. The horizontal hyperbola will have a standard form equation in the form of x minus h squared over a squared minus y minus k squared over b squared equals 1. Hyperbolas, as I just pointed to you out in the previous clip of this video, is found by taking these three-dimensional cones and cutting those cones parallel to their axis of rotation. So you get these asymptotes that help guide the graph, help guide the direction of the hyperbolas. It's effectively like the sides of those cones that you just sliced. When you graph a hyperbola, you're going to plot the center from pulling the x and y of the center out of the equation. You're going to draw a rectangular box, and through the corners of those boxes you're going to draw some asymptotes. So let's talk about all these pieces. From the center of the hyperbola, since my x is in the positive fraction, we're going to go left and right a distance of a. We're going to square root that bottom positive denominator, and we're going to find the vertices. We're going to move perpendicular to that, and we're going to move up and down a distance of b, and that comes from square rooting the denominator in the negative fraction, and we're going to move left and right a distance of c. So a still goes from center to vertex, b still goes from the center to this perpendicular direction, and c will go to the focus points. We draw these asymptotes, and because again the x is in the positive fraction, we're going to draw some horizontal opening hyperbolas passing through those vertex points and approaching the asymptote lines. And the hyperbola is the only equation that has asymptotes, the only conic section, that has asymptotes. Let's compare this graph and this information to ellipses. This standard form looks just like the standard form of an ellipse, except your middle sign is negative. So if you have where one fraction is positive and one fraction is negative, where they have different signs, you'll orient it so that the positive fraction is first, the negative fraction is second. And so that little sign change will sort of take your ellipse that we kind of were just looking at and blow it inside out, kind of. Your relationship between a, b, and c with an ellipse was c squared equals a squared minus b squared, but this sign change for hyperbolas will also cause you a sign change in that little equation to relate a, b, and c together. So it's c squared equals a squared plus b squared. In an ellipse, a is bigger than b. A comes from the largest denominator and b comes from the smallest. That's why we have these names for the axis of major and minor axis, where the major axis is always the longest axis. We lose that size relationship with hyperbolas. Now a comes from the square root of the positive denominator. So my positive fraction has the variable of x in it. That's why this is opening up horizontally. And if I square root that denominator, I have the value of a. When I square root the other denominator, I have the value of b. This difference here, where we're not relating a and b together based on their size, but based on what fraction underneath, a can be bigger than b, a can be equal to b, or a can be less than b. So instead of using major and minor axis as our names for our two axes, or axi, from vertex to vertex is called the transverse axis, and the length of the transverse axis is equal to 2a. The perpendicular direction, when we go up and down a distance of b, that entire length is going to be 2b, and that is the length of the conjugate axis. So there's a good breakdown, I hope, that you find for horizontal hyperbolas. If our hyperbolas are vertical, then y is going to be in our positive fraction. A is still going to come from square rooting the positive denominator, or the denominator of the positive fraction. Our asymptotes, instead of having slopes of plus or minus b over a, where we move up to the end of the conjugate axis, which is not a vertex, so thus it's labeled b. Instead of the asymptotes having a slope of plus or minus b over a, our asymptotes are going to have a slope, down here, a slope of plus or minus a over b. You know, when you move from the center and you go to the vertex, that's labeled as a, not b, just like with an ellipse. And that's pretty much it. This is the length 2a, transverse axis. 2b is the length of the conjugate axis. And before I just finish this video up, I told you about, in an ellipse, if you want to draw a perfect ellipse, you took a couple of tacks, a loose piece of string, pulled that pencil tight, draw it around, boom, perfect ellipse. That's because d1 plus d2 is a constant, and it's equal to the length of the major axis in an ellipse, or 2a. Well, the focus points in a hyperbola work together to shape the graph as well. But instead of d1, when you go from focus to graph to focus, instead of the sum of those distances being constant, the difference is constant. And the difference, you know, it's subtraction instead of addition like with an ellipse, but the difference is a constant as well, and it is also equal to 2a. Except now instead of 2a being the length of the major axis, it's the length of the transverse axis. So, that's a horizontal hyperbola, that's a vertical parabola, vertical hyperbola, and let's get some examples done. Bam! Woo! I love this stuff. So here we have our first of three examples. X minus 4 squared over 9 minus y squared over 1 equals 1. This is already in standard form, so as soon as we pull a little bit of information out of this equation, we'll have the graph. And we'll also need to make sure that we list off all the important information like the center, vertexes, or vertices, the foci, and the asymptotes. So let's start with identifying why is this a hyperbola. It's because we have two squared terms and our signs are different. One is positive and one is negative. If they were the same sign, then we would be dealing with an ellipse or possibly a circle if it was put up in a form to look like an ellipse, because a circle is, again, a special form of an ellipse. So A is going to come out of, or be found by taking the square root of 9, which is equal to 3, and B is going to be the square root of 1. Now, in this example, A does happen to be larger than B, but remember, that rule about that A must be larger than B is only true for ellipses. In hyperbolas, A comes from square rooting the denominator of the positive fraction. So we have A is equal to 3, B is equal to 1, and now let's find out what C is equal to. C is squared is equal to A squared plus B squared, or we're going to have C is equal to the square root of A squared plus B squared. We know what those values are. So we're going to have A squared, which is 9, plus B squared, which is 1. So C is going to be equal to the square root of 10, which we know is a little bit larger than 3, and it's actually equal to 3.16. Which I'm just going to round off to be 3.2 because we're, just sketching a hyperbola. But it is 3.16, and then it keeps going anyway. So somewhere there's always going to be round-off error with square rooting non-perfect squares. So we have A, B, and C. Now, from this equation, we can also tell what the direction is that the hyperbola is, if you can hear that, my coffee's almost ready. We have A, B, and C. So we can also tell what direction our hyperbolas are opening in. Our positive fraction has an x in it. So the fact that our positive fraction has an x in it means these hyperbolas are going to be opening up, let's just say, horizontally, like that. If you know what the slope of the asymptotes are already, when your hyperbolas are opening left and right, you may be able to write the equation of the asymptotes right now. I'm going to do the drawing first because I'm very visual, and I'm also going to help use that to reinforce exactly, is it b over a for the slope or is it a over b? We're going to use the picture to back that up. So before I get the picture done though, I still need to know where the center is. So the center is equal to the x of the center comes out from the x of the equation and the y with the y. So it's going to be, remember, the standard form is x minus h. So we're going to change the sign of these values as we pull them out. So the center is going to be equal to 4, 0. All right, let's get this graph drawn. My yellow chalk is shrinking up here, so let me go to blue. Our center is at 4, 0. So over to 4, 0. I'm going to put just a blue dot there for the center. All the other points I'll put a V for vertex or an F for focus point. I could put C for the center. And the A value of 3, what are we going to do with the 3? The same thing we did with ellipses. The 3 came from square rooting the denominator that was underneath the x. X is a horizontal axis, so thus we're going to go left and right 3 units. So left 3 and right 3. And that's going to give us our vertices. And the value of C, which is 3.12, or excuse me, 3.16 or 3.2, we are graphing a hyperbola. Remember, I just said this a second ago. They open out from each other. In this case, they will be horizontal. So your focus points should be farther from the center than your vertices are. If they've not, you've made a mistake. So we're going to go left and right 3.2 units. So let's do a different color for this. Left 3.2, I'm going to basically make that like 3.5 because I made my graph a little small here. And a little bit beyond that, vertex. So those are going to be our focus points. And now we've got this value of b, which is 1. So we're going to pick another color. And the square root of this denominator is 1. It's from underneath the y-axis is vertical, so we're going to go up and down 1. So from the center, down 1, and, well, my C is going to be in my way, and up 1. No real name for that axis, just going to go up and down 1. And now we're going to draw an imaginary box through these green dots, and the blue dots represent our vertices. Maybe should have weighted the graph, the foci, until after I was done drawing the box. Now this box is not the graph. This box is just being drawn to help you, make sure that your asymptotes go in the right direction. So okay, it's the best I can do. And so there we have our box with our asymptotes going through the corners. Let's go ahead and find the asymptotes now that we have these. Our common point for our asymptotes, of course, is the center. That's our common point, and the slope. When I go from the center up to the box, again, I'm not going to a vertex. I'm going to just sum this point in space. And then I go over to the right 3 units, which is going to take me into the direction of the vertices. So my slope for these asymptotes is plus or minus 1/3, or again, for horizontal asymptotes, your slopes are going to be plus or minus b over a. So it's going to be, again, plus or minus 1/3. So our asymptotes are y minus the y of the center equals m, and 1 up and 1 down, so plus or minus 1/3, and then x minus the x of the center, so x minus 4. So that's going to be our asymptotes. And then finally, our graph is going to pass through the vertices and approach the asymptotes. Do not pull your hyperbola away from your asymptotes lines. An asymptote is a line the graph approaches but does not touch. It's not a line the graph pulls away from. So that is the graph of our first example, our horizontal hyperbolas. Next one will be a little bit tougher, and then the last one is going to be an equation where I'm going to give it to you in general form. We're going to put it into standard form by completing the square, and then get the graph. Bam! Whoa! Before we go on to the next example, I never listed off all the information that I said you would need to do. Now we have the asymptotes, we have the equation for those, we have the center, but we never listed off the vertices and the foci. So the vertices, well, let's see, our vertexes, or our vertices, are equal to, we have one at 1, 0, and we have another one at, this is 1, 2, 3, 4, 5, 6, 7, 0. So you can write these important points as two separate coordinates like I have, or, as I'll show you with the foci, we have the center, which again is at 1, 2, 3, 4, 0, and the graph is moving horizontally. And of course, if you move left and right, you change the x values. So the foci are c units away from the center. So you can go, well, I want to move left and right. Well, that's going to make the x smaller and the x bigger. So 4 plus or minus the square root of 10, comma, 0. Now we're done. And as a comment here, as I looked at this information of A, B, and C, I drew the picture and came up with all the important information. I'm very visual, so you might have noticed that I didn't talk about all those little, I didn't say like the focus points are, oh, I don't know, H plus or minus C, comma, K when it's horizontal, and H, comma, K plus or minus C when it's vertical. I mean, if you draw the picture first, don't we know how to plot points? Don't we know that when you move left and right, that you change the x values, and when you move up and down, you change the y values? Now, you may not be very visual like I am, but I feel like drawing the picture first and then coming up with all these little values of vertices and foci and the center and the asymptotes saves you from having to memorize. There's still a lot of memorization, but not quite as much memorization where you have to memorize all those little tiny H and K formulas using A, B, and C and whatever else, okay? So there you go. Now our second example is coming up. This equation of a hyperbola is in general form. Now, there's no single degree term, so we're not going to have to complete the square or do very much work to get this into standard form. Just have to move a couple of numbers around and get the equation equal to 1. However, once you take your quiz, you are going to have to look at a collection of equations in general form, and it's a good idea to know what you're graphing before you start. So we have two squared terms, and again, their signs are different. So we have a hyperbola, and at this point the y squared term is positive, so it looks like it may be going up and down, but we can't tell that really the direction until we have it in standard form. So actually, let me change it a little bit just to give you that example. I look at this. Positive squared term, negative squared term. Hey, it's a hyperbola. The y squared is positive, so this thing's going to go up and down. I can't draw that conclusion yet. So here's why. We're going to get these squared terms alone, move the 100 to the other side with subtraction. So we're going to get 25y squared minus 9x squared equals negative 100. Now this is not in standard form until you get the equation set equal to 1. So we're going to divide everything by negative 100. That is going to cause a sign change, and we get, this is going to be negative y squared, and 25 over 100 reduces to 1/4. Or if I flip this down and say the denominator is 100 divided by 25, it's still going to be 4. And then negative divided by negative is positive, so we have plus x squared over, Now this one, 9 does not cancel out with 100. So we're going to go ahead and flip that down and say that it's 100 divided by 9. Right? I mean, if you divide by 2, like that whole number down here, well, this isn't 2, but if you divide by 2, that's the same as multiplying by a half, right? So if you multiply by half, that's the same as dividing by 2. So you can take this ratio and flip it down. And then this is going to equal 1. So the graph that we're about to work on, well, Here it looked like it was going to open up and down, but because I divided by negative 100, my equation of this hyperbola in standard form is actually x over 100 divided by 9 minus squared minus y squared over 4 equals 1. And I did intend to actually have this equation or this graph actually, go vertical, to do another example where one was horizontal, the one I just did, and this one's vertical. But I think this idea of seeing the sign switch is more important. So we're going to graph this. So again, we have a hyperbola opening, because the x is in the positive fraction, we again have a hyperbola opening in the horizontal direction. There is no plus or minus inside of any parentheses. It's just x squared and y squared. So the center is going to be 0, 0. We have an a value. Comes from the square root of 100 over 9. Don't grab your calculator, right? I mean, we can do the square root of 100. It's 10. And the square root of 9 is equal to 3. I'm going to leave that in exact form, but we know that's 3.3 repeating. B is going to come from the square root of the denominator under the negative term. So the b is going to be the square root of 4, which is equal to 2. And again, I have my a value bigger than my b. That does not have to be the case. That's only for ellipses where a has to be bigger than b. And c is equal to the square root of a squared, which is going to be 10 over 100 over 9, plus b squared, which is 4. Now, the 4 is over 1. We're going to have to multiply top and bottom by 9 to keep the common denominator. So c is going to be equal to the square root of, let's see, 100, 4 times 9 is 36, so 136 over the common denominator of 9. So my c value, that's all fine and dandy, and we can say this is equal to the square root of 136 over 3. I'm not really sure if there's a perfect square in that or not. I guess I could have done that in my scratch work. But for the graphing purposes, we really need the decimal. So c is going to be equal to approximately 3.9. Little squiggly line for approximate because we rounded off. Okay, so if I have center A and B and C, we can draw the hyperbola, and then we'll come up with all the important information. So my center is at 0, 0. My a value is 10 over 3, or 3 1/3. And a came from underneath the x, so we're going to go left and right 3.13. And b is 2, and that came from square rooting the number underneath the y, so we're going to go up and down 2. I'm going to go a little bit faster this time. Draw our little imaginary box that's going to help us draw the asymptotes in the right direction. So let's see if I can make this a little bit better than last time. Okay, so those are my asymptotes. Oh, got a little crooked there. And my focus points are 3.9 units away. Well, do I go up and down 3.9 units or left and right 3.9 units? C, like A, goes in the direction of the transverse axis. And again, our hyperbola has x in the positive term, so this is a left and right hyperbola, or horizontal hyperbola. So we're going to go left and right 3.9 units for the focus point. So 1, 2, 3.9. Your focus and your vertices are not always as close together, but they do need to be on the outside of the vertices. And my graph looks like this. Through the vertex and up towards and down towards your asymptote lines. So now that we have the graph drawn, or you could do yours before, try not to make them look like V's. We have, let's see, we already have the center. Let's get this out of the way. We have, probably needed that C value. we have the center of 0, 0. We have vertices of, from the center we moved left and right 10 over 3. So our vertices are negative 10 over 3, 0, and positive 10 over 3, 0. And our foci are plus or minus the square roots of 100 over 9, comma, or, ooh, that's not what they were. What was that value again? Square root plus or minus square root of 136 over 3, or we can just do, let's just do plus or minus 3.9, comma, 0. Now your asymptotes, again, common point is the center, so point slope form, so y minus the y the center, which is 0. That's only for academic, you don't really need to write minus 0. Plus or minus. Horizontal, the slopes are b over a. If they were vertical hyperbolas, it would be a over b. But anyway, with the graph we can say it's 2, let's do it in fraction form. 2 over the horizontal movement, a of 10 over 3. Was a 10 over 3? Yeah. And then x minus the x of the center. What the heck am I supposed to do with this slope, this, like, you know, fraction within a fraction slope? Well, remember, a fraction bar means division. So this is 2 divided by 10 over 3, which is equal to 2 over 1 times 3 over 10, and that is equal to 6 over 10. It's always that bottom fraction that you're dividing by. So it's always that bottom fraction that you're going to have to flip to change your division into multiplication, and this will reduce down to 3/5, which is why in my classes, when I have a fraction over a fraction, I always do this sort of dumb pigtail, little pigtail movement to remind the students to flip the bottom up. And our asymptotes finally are y equals plus or minus this reduced 3/5 x. Bam! Let's get on to the next example and the last example. For our last example, we have a hyperbola in general form, but we have single degree terms in both the x and y variables. So we're going to have to complete the square twice to get this into standard form, just like we did with ellipses. So we're going to get our constant, move over to the other side of the equation. So we're going to add 144 to both sides and get 9y squared plus 36y minus 4x plus 24x, that was x squared by the way, equals 144. Now, we have a couple of issues. We cannot complete the square unless our leading coefficients are equal to 1. And please, as you're completing the square, do not forget that you're factoring out a negative 4 for the x terms. So don't make a sign mistake. Don't forget that you have a negative there. So we're going to factor a 9 out of the two y terms, and we get 9 divided by 9 is 1, so we have y squared. 36 divided by 9 is 4. I'm going to leave room for completing the square because our leading coefficients are now 1. And we're going to factor out that negative 4. So negative 4, and then negative 4 divided by negative 4 is equal to 1x squared. Positive 24 divided by negative 4 is negative 6x. Leave some room for completing the square, equals 144. Now, my example here, has a negative 4. If your equation has just a negative sign there, so it'd be like negative x squared, you might want to put in a 1 there to remind yourself that it is negative 1x squared, or whatever you have in your equation, so that you factor out that negative 1. So, but we have a negative 4, so we factored out negative 4. Now we're going to complete the square, so we're going to take half of b, the number that's in front of the single degree term, so we're going to do 4 divided by 2, square that value, so that's 2 squared is 4, and add 4 to the left, and that means we're going to have to add 4 to the right. Now let's not forget there are 9 of these groups. We had a factor out of 9, so it's going to be 4 times 9 on the right-hand side. Half of negative 6 squared, well, that's going to be negative 3. Negative 3 squared is 9, so add that 9 to the right-hand side. And again, do not forget that value that you factored out of the group, which was negative 4. So that's going to be 9 multiplied by negative 4. And again, don't forget that negative sign. So we've just made some perfect square trinomials, so we're going to square root the first term, square root the last term, and keep those middle signs when we factor these perfect square trinomials. So we have 9 times y plus 2 squared minus 4 times x minus 3 squared, and then equals over here, we've got positive 36 from 4 times 9 and negative 36 from 9 times negative 4. So these are just going to cancel out. And we get 144. And our last step to get this hyperbola into standard form is to divide everything by divide everything by 144. And get our equation in standard form, and that's going to be y plus 2 squared over (16) minus x minus 3 squared over 36 equals 1. Now I've taken up all my empty space to get my equation from general form into standard form. So let's take a pause. I'll erase this, get the standard form written up here, find all the values of A, B, and C, asymptotes, vertices, foci, whatever. Get that graph drawn. Woo! Okay, this one is going to open up vertically. So A is going to be the square root of the positive denominator, so A is going to equal 4. B is going to be the square root of 36. And in this case, A is smaller than B. No big deal with hyperbolas. C is the square root of A squared plus B squared. So it's going to be the square root of 16 plus 36, or the square root of 36, 46, 52, which is going to be equal to 4 times the square root of 13, or 2 square root of 13, and that is equal to, for graphing purposes, 7.2, approximately. Okay, so I have A, B, C, and the center, actually let's put that over here. The center is 3, negative 2. All right, let's get this drawn and finish this video up. So, we have a center at 3, negative 2. From there again, we go, 4, 16, up and down 4. And we go left and right 6 units, so 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Yep, and draw a little box, which in this case is actually rather a large one. Draw our asymptotes through the corner of that rectangular box. Not the graph itself, just a guide. Let's make a note again that this hyperbola is opening in a vertical direction because y is in the positive fraction, so these are going to be our vertices, which we'll highlight in a second in our list of information. Well, another highlight in the graph. And our hyperbola is going to go through those vertices and again up towards your asymptotes. And again, you are not going to pull those hyperbolas away from those asymptotes. The focus points, which are 2.7 units away from the center of the graph, are going to as well be in a vertical direction because it's a vertical hyperbola. So we're going to go up and down 7.2 units. So 1, 2, 3, 4, 5, 6, 7, almost running out of room there. And 1, 2, 3, 4, 5, 6, 7.2. So that means our center is at 3, -2. Our vertices, let's change that color. Our vertices are at 3, 2, and 3, 2, 3, 4, 5, 6, so 3, -6. And our foci, or foci, is equal to, let's see how, 3, -2, plus or minus 2 square root of 13. And the only thing I haven't brought up yet are the asymptotes. The asymptotes are y minus the y of the center, which is -2, equals plus or minus. Now we're going up and hitting the vertex, so it'll be plus or minus a over b. So it's going to be plus or minus 4 over 6, which reduces to 2/3, times x minus the x of the center, which is 3. I'm Mr. True. There's your 3 examples. Bam! Go do your homework.